Folks, a few days ago I met a friend on the subway. He tells me he's been at a conference and someone asked if he knows me. He says yes, and immediately people start complaining about me. One guy apparently told him to slap me. What were they complaining about, you want to know? Well, one complaint came from a particle physicist who was clearly dismayed that I think building a bigger particle collider is not a good way to invest $40 billion. But it was true when I said it the first time, and it is still true. There are better things we can do with this amount of money, such as, for example, make better climate predictions, which can be done for as little as $1 billion. Check links below the video for more information on that. But back to my friend on the subway. He told me that besides the grumpy particle physicists, there were also several gravitational wave people who have issues with what I have written about the supposed gravitational wave detections by the LIGO collaboration. Most of the time, if people have issues with what I'm saying, it's because they do not understand what I'm saying to begin with. So with this video, I hope to clear the situation up. Let me start with the most important point. I do not doubt that the gravitational wave detections are real. But I spend a lot of time on science communication, and I know that many of you doubt that these detections are real. And to be honest, I cannot blame you for this doubt. So here's my issue. I think that the gravitational wave community is doing a crappy job justifying the expenses for their research. They give science a bad reputation. And I do not approve of this. Before I go on, a quick reminder what gravitational waves are. Gravitational waves are periodic deformations of space and time. These deformations can happen because Einstein's theory of general relativity tells us that space and time are not rigid, but react to the presence of matter. If you have some distribution of matter that curves space a lot, such as a pair of black holes orbiting one another, these will cause space-time to wobble, and the wobbles carry energy away. That's what gravitational waves are. We have had indirect evidence for gravitational waves since the 1970s, because you can measure how much energy a system loses through gravitational waves without directly measuring the gravitational waves. Hulse and Taylor did this by closely monitoring the orbiting frequency of a pulsar binary. If the system loses energy, the two stars get closer and they orbit faster around each other. The predictions for the emission of gravitational waves fit exactly on the observations. Hulse and Taylor got a Nobel Prize for that in 1993. For the direct detection of gravitational waves, you have to measure the deformation of space and time that they cause. You can do this by using very sensitive interferometers. An interferometer bounces laser light back and forth in two orthogonal directions and then combines the light. Light is a wave, and depending on whether the crests of the waves from the two directions lie on top of each other or not, the resulting signal is strong, that's constructive interference, or washed out, that's destructive interference. Just what happens depends very sensitively on the distance that the light travels. So you can use changes in the strength of the interference pattern to figure out whether one of the directions of the interferometer was temporarily shorter or longer. A question that I frequently get is how can this interferometer detect anything if both the light and the interferometer itself deform with spacetime? Wouldn't the effect cancel out? No, it does not cancel out, because the interferometer is not made of light. It is made of massive particles and therefore reacts differently to a periodic deformation of space-time than light does. That's why one can use light to find out that something happened for real. For more details, please check the information below the video where I have references. The first direct detection of gravitational waves was made by the LIGO collaboration in September 2015. LIGO consists of two separate interferometers. They are both located in the United States, some thousand kilometers apart. Gravitational waves travel at the speed of light, so if one comes through, it should trigger both detectors with a small delay that comes from the time it takes the wave to travel from one detector to the other. Looking for a signal that appears almost simultaneously in the two detectors helps to identify the signal in the noise. The first signal measured by LIGO looks like a textbook example of a gravitational wave signal from a merger of two black holes. It's a periodic signal that increases in frequency and amplitude as the two black holes get closer to each other and their orbiting period gets shorter. When the horizons of the two black holes merge, the signal is suddenly cut off. After this follows a brief period in which the newly formed larger black hole settles in a new state. That's called the ring down. A Nobel Prize was awarded for this measurement in 2017. If you plot the frequency distribution over time, you get this banana. Here it's the upward bend that tells you that the frequency increases before dying off entirely. Now, what's the problem? The first problem is that no one seems to actually know where the curve in the famous LIGO plot came from. You would think it was obtained by a calculation, but members of the collaboration are on record saying it was not found using analysis algorithms, but partly done by eye and hand-tuned for pedagogical purposes. For reference on these quotes, please check the information below the video. Both the collaboration and the journal in which the paper was published have refused to comment. This, people, is highly inappropriate. We should not hand out Nobel Prizes if we do not know how the predictions were fitted to the data. The other problem is that so far we do not have a confirmation that the signals which LIGO detects are in fact of astrophysical origin and not misidentified signals that originated on Earth. The way that you could show this is with a LIGO detection that matches electromagnetic signals, such as gamma ray bursts measured by telescopes. The collaboration had so far one opportunity for this, which was an event in August 2017. The problem with this event is that the announcement from the collaboration about their detection came after the announcement of the incoming gamma ray. Therefore, the LIGO detection does not count as a confirmed prediction, because it was not a prediction in the first place, it was a post-diction. It seems to offend people in the collaboration tremendously if I say this. So let me be clear. I have no reason to think that something fishy went on, and I know why the original detection did not result in an automatic alert. But this isn't the point. The point is that no one knows what happened before the official announcement, besides members of the collaboration. We are waiting for an independent confirmation. This one missed the mark. Since 2017, the two LIGO detectors have been joined by a third detector called Virgo, located in Italy. In their third run, which started in April this year, the LIGO-Virgo collaboration has issued alerts for 41 events so far. From these 41 alerts, 8 were later retracted. Of the remaining gravitational wave events, 10 look like they are either neutron star mergers or mergers of a neutron star with a black hole. In these cases, there should also be electromagnetic radiation emitted, which telescopes can see. For black hole mergers, one does not expect this to be the case. However, no telescope has so far seen a signal that fits to any of the gravitational wave events. This may simply mean that the signals have been too weak for the telescopes to see. But whatever the reason, the consequence is that we still do not know that what LIGO and Virgo see are actually signals from outer space. You may ask, isn't it enough that they have a signal in the detector that looks like it could be caused by gravitational waves? Well, if this was the only thing that could trigger the detectors, yes, but that is not the case. The LIGO detectors have about 10 to 100 glitches per day. The glitches are bright and shiny signals, but do not look like gravitational wave events. The cause of some of these glitches is known, the cause of other glitches not. LIGO uses a citizen science project to classify these glitches and has given them funky names like Koi-fish or blip. What this means is that they do not really know what their detector detects. They just throw away data that don't look like they want it to look. This is not a good scientific procedure. Here's why. Think of an animal. Let me guess. It's an elephant, right? Right for you, not right for you? That's a glitch in the data, so you don't count. Does this prove that I'm psychic? No, of course it doesn't, because selectively throwing away data that's inconvenient is a bad idea. Goes for me, goes for LIGO too. At least that's what you would think. If we had an independent confirmation that the good-looking signal is really of astrophysical origin, this wouldn't matter. But we don't have that either. So that's the situation in summary. The signals that LIGO and Virgo see are well explained by gravitational wave events. But we cannot be sure that these are actually signals coming from outer space and not some unknown terrestrial effect. Let me finish by saying once again that personally I do not actually doubt that these signals are caused by gravitational waves. But in science, it's evidence that counts and not opinion.